Good morning, good afternoon, and good evening to all of you. I can see we've got some attendees from across the globe here today, so that's absolutely wonderful. Thanks so much for joining us. My name is Shannon Holmes. I'm a medical physicist at Standard Imaging, and it's my pleasure to be able to talk to you today about some of the nuances and challenges of small field dosimetry. Thanks for joining as well the Astro Vendor Day. We really appreciate your support of vendors at these meetings as well. So, first of all, I just want to stop and say thank you to all of you. We know cancer doesn't get put on hold even in the middle of a pandemic. So we really appreciate all of the efforts that you and your teams are making to treat the patients in your clinic. We know your time is precious. We want to help you make the most of it. So a little bit of housekeeping before I really get into the meat of my talk today. I am recording the webinar. We will send it around to you so that you can review the parts you've missed or want to go back and see. Or if you'd like to forward it on to a colleague, that's perfectly acceptable too. If you have questions at any time during my presentation, please go ahead and enter them into the GoToMeeting dialog box. I'll try and answer them as I go along, but if I don't get them in the middle of the presentation, I will certainly circle around to them back. If you don't know much about us, Standard Imaging is based in Middleton, Wisconsin. We're just outside of Madison. We were founded in 1989 with kind of a modest couple beginning products. But in the intervening 31 years, we have grown significantly to now be designing and manufacturing a full suite of QA products for radiation therapy. So, back to small fields. What really makes small fields so challenging? First and foremost, seems a little strange to say it, but it is the size. Size is tricky when you get down to these very small fields. A few other things that I will be touching on these more as we get into the talk. But a few other things that really affect small fields, make them troublesome, are things like source occlusion, energy changes in your field as the fields get smaller compared to your reference field sizes, changes in the shape of the penumbra, loss of your lateral charge particle equilibrium. And a lot of the stuff that I'm pulling from for this talk came from a couple of very excellent references. The first one here, the book cover shown on the left, is the IPEM Report 103, which is the small field MV photon dosimetry report. And a slightly more recent one, but also extremely good. It was a joint publication by the IAEA and the AAPM that is Technical Report Series number 483. And that title was Dosimetry of Small Static Fields Used in External Beam Radiotherapy. I highly recommend both of these if you have not looked into them. They're a little daunting. Well, this one in particular is a little bit daunting as you first download it, but they are extremely useful. So, conditions for small fields. What makes a small field? TRS 483 defines small fields as meeting at least one of these three conditions. Number one, loss of lateral charge particle equilibrium on the beam axis. Number two, partial occlusion of the primary photon source by the collimating devices on the beam axis. And number three, the size of the detector is comparable to, similar to, or large compared to the beam dimensions. If you have any one of these conditions, then you are measuring small fields, or you are in that area of small field dosimetry, and so you need to make consideration for a lot of these various factors that affect your measurement when you have these conditions. So, challenges. First one I mentioned is physical size. Generally, for TRS 43, for the physical size of small fields is in the range of 4 to 40 millimeters. In that range, we're looking at a little bit of a mismatch in how we define the fields. Are you saying the name of where the jaws are, or are you actually looking at the position of the full width half max for the penumbra? Because as you decrease your field size, this is a figure from a publication by Indra Das et al. If for a normal field size, your jaws and your 50% penumbra location match, as you go smaller, you reach a point where the full width half max actually gets larger than your jaw setting, just because of the way each side of the field is shaped by the jaw on that side, or the MLC, whatever it is that is shaping it. They both have similar effects. And then once you get small enough, you have a very significant difference between where these blue arrows show the jaw locations and the broader shape of this profile, just due to those penumbra effects. So you need to be aware of exactly how those field sizes are defined, especially if you're comparing to somebody else's measurements. Are they talking about the actual field size, or are they talking about the machine settings for the field size? You get, as you can see, a decreased output, which we know from the output factors we've been measuring for years, that as you get smaller, you get this decreased output as well. But it is, of course, much more pronounced when you get into these small fields. The other thing that really matters, as I'm sure you're all aware, when you get down to these very small physical sizes for the fields, is alignment of your detectors. If you have a very small mismatch in a large field, it doesn't really affect your measurement too much, and so your uncertainty is pretty reasonable. In a very small field, your positioning uncertainty plays very heavily into your measurement uncertainty, because a very small misalignment can be a very large geometric or dosimetric miss or error. One of the second the second one I've listed, I guess, as the small field challenges is source occlusion. And this is an image from that IPEM report that I showed you at the beginning. In a large field, you see essentially at the measurement point, you see the whole distribution of where that source field is being generated. As you get to these smaller fields, some of that gets blocked. Some of that view of the source gets blocked by your collimation system. And that's what we call source occlusion. And so you have a portion maybe where you can see the whole source, but very close to the side, you may not be seeing that full source. That changes the scatter conditions. So scatter from your primary collimator and your flattening filter, if you're using one, is reduced. But even the direct beam fluence can be reduced by the collimation system if your field is small enough. The next challenge, lateral electronic equilibrium. Generally, the equilibrium condition is when your lateral scattering distance is equal to or greater than the range of the electrons that are generated by that energy beam. Practical translation of this definition is that you may start losing your lateral equilibrium when your beam width is less than 2 times your Dmax. And this is not really counting the size of your detector just yet, because if you're changing the fluence with your detector, that exact equilibrium condition width may change slightly, but it's a good rule of thumb to start with. And generally then, because of that condition of being less than twice your Dmax, your higher energy beams are going to lose this flat plateau, the flat center of the field, or flat-ish if you're talking FFF, sooner than the lower energies will. So you actually hit small field conditions earlier on a higher energy beam as you're going down in field size than you do with a lower energy beam. So your detector positioning comes into is critical. That issue comes into play sooner for those higher energies. It also means that it's important to characterize the profiles of your beams and to understand how that changes for your machine, not just measuring the output factors at the center. So then the detectors themselves can impact your measurements as well. So detectors, one of the first ways that I usually talk about, detector size and shape is the first factor that to consider when you're looking at the impact of the detectors on your measurement. So there's always some volume averaging that's happening with a detector. There is no such thing as a perfect point detector. So you need to understand your detectors. And for something like ion chambers, you need to understand if your spot size for your chamber is spherical, So the orientation within this profile doesn't matter so much. Or if you've got an elongated profile for the spot size of your detector, the area over which it's measuring, in which case the integration over the field transverse to your detector compared to in line with your detector is different. And so your volume averaging, depending on the size of your fields and where you're making those measurements, will affect your measurements as well. The size of your detector also determines how accurately you are measuring your beam penumbra, because obviously a larger detector, larger integration in the direction of the penumbra will include a little bit bigger smearing effect, a little more averaging as you're measuring that penumbra. Consistent and accurate positioning is critical, obviously, with your detectors. And if you're using film, in some cases, usually it's in very, very small fields. I think I've only really seen this much in brachytherapy, but I think it should be considered when we're looking at extremely small fields. The scatter within the film scanner can also affect how good your resolution is for your measurements. So I just wanted to explain a little bit about the plot that I'm showing here. These are profiles for an older gamma knife. And the chamber that was used, this is a publication from Meltzner and Diode about 11 years ago, but they were looking at output factors for these various gamma knife helmets. And initially, we're looking at the 4mm helmet being the only one that really ought to need some corrections for the volume averaging and small field effects. But once you consider the fact that the chamber is not just the active area, it also involves the side scatter for the buildup on either side, or the shell of the chamber. You see that your small field might be a little bigger than you think small fields are. Sorry, your small field conditions are seen at a larger field than you may have thought they would be, just based on that interior dimension of the chamber. Another way that detectors impact the measurement is by perturbing the beam. You're actually changing the way that the irradiation interacts right there at the point of measurement. You're altering the dose by replacing water with whatever detector you have, whether that's an ion chamber or a diode or something more like a scintillator or a diamond detector. So the things to ask when you're looking at these detectors, for something like an ion chamber, how big is the air cavity? How is that going to affect the size limitations where you can measure? For a diode, you need to look obviously at density corrections. Diodes are more dense than water. But other things to question about diodes is whether or not they're compensated diodes. Oftentimes for a compensated diode, there's an air gap that's added in order to effectively compensate for the increased density of the diode with a decreased density section of air. Those are great at the energy and conditions where they were designed, but it is very good to investigate whether or not your compensated diode is really appropriate for the conditions you want to measure with, because they can actually become a little bit more complex for some of those situations. So something to be aware of, something to ask about. There are often published corrections available. This plot here is from Paulo Franciscan that shows some various beam quality correction factors for some ion chambers, liquid chamber, compared to diodes. So here you do see, below 2 centimeters or so, 1.5 centimeters, we get the increased correction factor for these decreased density detectors, and a correction factor below 1 to account for the over response of the higher density detectors. The thing to be aware of or be careful of as you're trying to match or trying to apply these published corrections is that oftentimes, in order for these corrections to be valid, you have to match the published measurement conditions as well. So be aware of whether something was done in an electron beam or a 6 MV photon beam or an FFF beam or a high energy beam, or water versus plastic, all of those sorts of things, or in air. All of those conditions can affect what you're looking at or the corrections that you might need to apply. A lot of that's in TRS 483 as well. That's very helpful in terms of matching published data with the conditions you have. This was a little more data from a different publication from Paulo Franciscan, looking at some additional correction factors. These were Monte Carlo simulations, both for diodes, for microchambers, the microlion that was a liquid chamber, for a 5 millimeter collimator. And you can see actually the Exradin W1 scintillator is the flattest curve up here. Another way that detectors impact measurements, signal. If you are using, say, an ion chamber, your signal is proportional to your collecting volume. So as we try and make smaller and smaller ion chambers, your signal level does go down, which means your signal to noise ratio becomes much more of a concern as you get to these smaller chambers. You need to be extra careful to make sure you're correcting properly for leakage and other issues that come along with that low SNR as well. Small signals also require an appropriately sensitive electrometer. You need to match the range and the capabilities of your electrometer with the signal levels that you're going to be seeing from your detector. A diode gives you a larger signal than from those microionization chambers, but of course has the trade-offs of the density and the energy dependence. I touched on this above, but another way that detectors impact your measurement is your SNR. So you do need to make sure that you give your electrometer a proper warm-up to decrease your leakage. Check your leakage, be aware of it, and don't perform measurements if it is too high. I guess I talked about matching signal strength with your electrometer range. If your electrometer auto ranges, be aware of that as well, because that can actually add a little bit of additional uncertainty if you bump across ranges, especially if it's not zeroing all ranges when you do your zero beforehand. And one thing I learned just in the past few years from one of our electrical engineers is that you can get some triboelectric effects from your triax cable, as well as obviously stem effects if you're irradiating the cable directly and you've got an older, not so good cable. Both the chamber and the extension cables can suffer from this, but the triboelectric effects are interesting. If you have a tightly wound cable and you unwind it and you just let it sit and relax for a while, it continues to drift a little bit if you're putting bias on it as that cable relaxes. So if you have a system that never holds at zero, think about your cable. Think about whether that was just recently unwound or if it's one that's been sitting in the raceway or you're commissioning a system and it's sitting there for a long time. It can take a few hours for a cable to relax if you're doing these. So if you are doing some of these highly sensitive small ion chamber measurements or small signal measurements, be aware of that as a potential issue. And then, of course, potentially cable-induced signal if you're irradiating a large section of the cable, which will manifest more as a stem effect, changing variation as you change field size. And then you need to know what the accuracy of your detector is. Does it have any energy dependence? We talked a little bit about diodes with their higher density causing a little bit of energy dependence just because of the different interaction within that higher density region, especially compensated diodes. Is that good or is that bad? But diodes can also have a low response out of field compared to the actual dose that's being delivered, and so can have occasionally underestimated a large region of low dose if you're commissioning and you're measuring those large tails and then using those values for your SRS calculations. You can underestimate that low dose region if you've only used a diode for the scanning. Because of the energy dependence, you may have corrections that are different at different depths because of the attenuation of the beam through the water above. And of course, changes in scatter condition affect the response because the scatter energies are a little broader spectrum usually than the beam itself. You can have angular dependence from your detectors. So the key there is to make sure you're using it in the orientation for which it was designed, or at least be aware of the implications of moving away from that orientation, the recommended orientation. There can be dose rate or dose per pulse dependence from your detector. This requires understanding both your accelerator and your detector. Some accelerators change the dose rate, just decrease dose rate just by dropping pulses rather than changing pulse height to go from one dose rate to another. But that's something that you would need to be aware of, how your system behaves, so that you know what sort of corrections you may need to apply for your detector. And there are others, smaller ones I haven't covered too much here. There's leakage not just of your electrometer, but potentially of your detectors. How repeatable are they? What's the resolution at which you're actually providing data for your field? Can your detector be calibrated? These are all questions to consider as you're trying to figure out what's best for your small fields. So after all that, what's a physicist to do? Sometimes it feels like you're just staring at a box, wondering if there's any solution anywhere. Sometimes it feels a little bit more like a ticking time bomb, because you've been told we're setting up an SRS or an SBRT program, and you need to commission the small cone. Thank you very much. And it feels like it's something that might blow up in your face if you don't get an answer soon. So we're here to help. I promise we're here to help. So I have 3 options to present right now for MV beams. One is established technology, although there are known perturbation issues. So I'm talking here about our diodes. The second one would be new technology, which would be the Exradin W1 and W2 plastic scintillation detectors. Actually, the W1's been on the market for quite some time now, so I don't know how long I get to keep using the word new. But it's new to a lot of people. There are a number of people who aren't familiar with it yet. And then there's, of course, the old standard, the ion chamber, which is finally working properly in miniature form in the A26 microionization chamber. So I'll tell you what I mean by that here in a moment, too. So every detector, whether you get it from standard imaging or you have something from somebody else, every detector has both strengths and limitations. The best solution you're going to find for your small fields is a good combination of detectors. So for our diodes, the D1V and the D1H, it's the same diode, just in 2 different orientations. So the horizontal version is really designed for use in a plastic phantom. The vertical version is designed for use in scanning, so your end on to the beam here. But inside, it's exactly the same diode. They're unshielded, and they have a 1 millimeter diameter spot size, and there are some published correction factors available for these. There's one from Papakonstantopoulos from 2014. I think there are a few others on our website. I didn't list them here, but this image is from that publication, looking at correction factors for the D1V, as well as the scintillator, actually. Strengths of the diode. Oh, and this is one from the Paolo Franciscan publication I showed earlier, where the diode is shown here in the green. Strengths of the diodes is that diodes are well-established technology. They've been around for quite some time now. You can use them for scanning. They give a nice big signal. There is some minimal volume averaging, just because of the 1 millimeter spot size, but it's smaller than your ion chambers, so it is nice for defining penumbras. And they have a fairly low angular dependence, although mostly if you're scanning with them, you're end on anyway, so that's pretty easy. Limitations are that no diode is water equivalent, so these are no different. So they do require some corrections for that density or for the energy changes, but that's where the publications come in handy. And there is, of course, some angular dependence. That's the way diodes are. So those are known limitations of any diode. The second option I'm presenting to you is our scintillation detectors. We have the W1, which has been on the market for quite some time. That is a 1 millimeter diameter, 3 millimeter long organic scintillating fiber. The more recent version of it, called the W2, has a dedicated electrometer called the Max-SD. That's the one that's shown down here. There are multiple fiber options with that one. You can get a 1 by 1 millimeter or 1 by 3 millimeter. Actually, I should say it comes with both. You can use either one, whatever is most appropriate for what you're measuring. The biggest benefit of the scintillators is that this organic scintillation material is water equivalent. The one of the tricky parts on why these weren't widely adopted until just recently is that when you're doing scintillation measurements like this, you have to account for the Cherenkov light that's produced in the optical transfer fiber. It manifests essentially as a stem effect, an extra signal that is generated depending on the field size, depending on how much of this extra fiber is irradiated. And so we do have a routine to help you correct for that. And then they're also not absolute dosimeters. So they do require a reference dose. You would cross-calibrate these with in a field with a known dose, either your reference 10 by 10 field, or if you're talking smaller fields, you might do a daisy chain more at 4 by 4 or 5 by 5. And they do need a periodic recalibration, both for the CLR, which is Cherenkov light ratio, and for a dose characterization as the material accumulates dose. It is a plastic, just as we've seen plastic phantoms yellow with age. As they're irradiated, the clarity of the plastic does decrease, which affects the spectrum that's transmitted through it. And so that both decreases your signal as well as changes a little bit of the balance between the scintillation and the Cherenkov light. So that's the reason for the recalibration. We apply a 2-channel chromatic correction. I thought I had, there are my equations. We do apply a 2-channel chromatic correction that's based on a publication from Matthew Guyot. Our scintillator is a blue scintillator. So this is a mock-up of what that scintillation signal looks like. Cherenkov is a broad spectrum contaminant light, and so we actually split the total signal into 2 components. We call it the blue channel and the green channel. So blue is primarily the scintillator with Cherenkov, and then the green is primarily Cherenkov with this tail of the scintillation light in it as well. And so in order to characterize the response, we have you do 2 separate measurements. This is the characterization jig that comes with the W1. We have a smaller one for the W2 that can be used in a water tank. But essentially, you do 2 measurements, one with the scintillation fiber coming straight out, and one with the, we call that the minimum fiber configuration, and one with the fiber wrapped all the way around in this channel, which we call the maximum fiber configuration. And you irradiate it with a larger field, like a 30 by 30 field, to cover this whole plastic phantom. For the smaller bracket that we use for the W2, you can do it in a 10 by 10. But the idea there really is you're keeping the dose to the scintillation, or to the active portion, the same, the dose to the center of the field here or wherever the tip of the fiber is, but changing the amount of Cherenkov. So this curve from the scintillator should remain constant, whereas this curve will shift up when you do your maximum fiber configuration. So then we take a look at the difference in the blue channel divided by the difference in the green channel for those 2 configurations, and that gives us this Cherenkov light ratio. With that, we can then correct subsequent measurements by subtracting from that blue channel signal a corrected value of, or proportion of, the green channel signal, and that removes the Cherenkov then from your measurement. If you want to do a dose calibration of this detector, that really is just a scaling factor that's inserted in here. So you can do a dose calibration with a reference field size, give it a known dose, and then you can get your scintillation measurement output in terms of dose. So I mentioned the W1 is the 1 millimeter diameter, 3 millimeter long scintillator. And in the TRS 483 publication, they have a lot of tables of correction factors for various energy beams as a function of field size. And in every single table where the W1 shows up, every single correction factor here is unity. And that's because we really are truly water equivalent for this detector. You'll notice some other detectors, as you get down, below 5 centimeters, you start to need corrections with a lot of those chambers or other detectors. And where the publication does not list values, it's because the uncertainty was too high and they didn't recommend that detector be used for those field sizes at all. So that's always a fun table to point out to people. I always enjoy that one. The strengths of the W1 are that KQ value of 1, as shown in the TRS 43 publication. It is water equivalent for megavoltage photons and electrons. We don't see dose rate or energy dependencies with this. There is a very small temperature dependence. It's about 0.1% per degree Celsius. But as long as you're doing all of your measurements at room temperature or close to room temperature, then there is no need to make that correction. Limitations of the W1, it's not designed really for scanning or for large fields. It is a small field detector. It does need to be used with a 2-channel electrometer like our Supermax. We have a scintillation routine built into here so that it will automatically do that Cherenkov calculation and correct your measurements for you. But you do need to have that 2-channel electrometer to work with it. The W1 has a low SNR, so there's a higher uncertainty in the dose out of field. If you were trying to do a point-by-point measurement of a field profile, you'll get a higher uncertainty for those out-of-field measurements. You will start bumping up against the electronic noise floor of the system. As with, we mentioned about the scintillation detectors, you do have to give it a reference dose and occasionally recalibrate it. The other issue that we found with the W1 is that optical signal measurements are not intuitive to many users. We're very used to measuring with ion chambers. We understand diodes, and so when things don't look quite right, we have an idea of where to look. Whereas measuring with optics like this, measuring optical signal, takes a little bit more getting used to for some people. It's not bad. You can get over the learning curve fairly quickly, but when things don't look quite right, it does take a little bit more troubleshooting sometime to figure out what's going on with that. With the W2, which is the 2nd generation device, we have improved our detection optics so that we can give you both a 1x1 millimeter detector and a 1x3 so that you can have that small field resolution. You can also have a higher signal device for scanning slightly larger small fields or for comparing with those published W1 measurements. There are dedicated electronics here that do both that optical signal collection and the 2-channel chromatic correction. That was part of what helped us go down to the 1x1 scintillator as well, because we could decrease our electronic noise floor with this integrated system. You can perform point measurements directly with the Max SD if you're trying to do output factors or something like that. But it also does a very fast Cherenkov correction and can convert that corrected signal into an analog output so that it can send it out to the electrometer on your scanning water tank, for instance, so that you can hook it up as a kind of a 2-stage intermediate there in the input channel of your water tank. And your water tank doesn't know that it's any different from a diode. You don't apply bias to it, but you get signal when it's irradiated. So we kept the strengths of the W1. We didn't lose anything with that, but we were able to cut out a couple of those limitations when we went with the W2. The old standard now working well, that's the Exradin A26. This microchamber was designed as a result of Jessica Miller's Ph.D. thesis investigation at the UW-Madison. She was looking at all microchambers that were available on the market and why they were showing such inconsistent and illogical behavior when you looked at your polarity response. And what she tracked it to was actually it was actually a conductance issue within the chamber that changed the electrical field and so would change the volume over which the chamber was actually collecting dose. And that was what this polarity issue came from. So this is a microchamber. I don't know which one, but one of the standard microchambers. And this is the plot of negative versus positive for the A26. And this wasn't an issue just with our microchambers. This was an issue across the board with every microchamber manufacturer. And it wasn't something that could be characterized by the type of microchamber either, by the brand or by the model number. It seemed to be very unique to the construction of each microchamber. So that was a fun puzzle to have her solve And then we could make use of it to make this this chamber. So it was designed to provide reference class measurements for your small fields to meet these conditions of what a reference class chamber is. So when we were designing it, then we had to ask ourselves questions like, what spot size can we get to? Does it matter if it's spherical, or could it be elongated? And we really did settle on the spherical being the best geometry, so that your orientation doesn't matter and your volume averaging is uniform no matter which direction you're scanning. We modeled the electric fields to make sure that we knew the volume precisely and we knew the shape of that collection volume. If we look at our smallest chamber, the A16, the measurement volume is 0.007 cubic centimeters, whereas the A26 just about, or a little over, doubles that with 0.1015. However, your spot size has gone up by less than a millimeter. 0.8 millimeters is all that we've added on the spot size for this one. So it's not a very big increase in spot size for a doubling of the signal, as well as better behavior. We made the chamber volume just as small as we can make it. I don't think you'll see a well-behaved chamber any smaller than this, just because of those electrical effects as well as manufacturing limitations. This is probably the smallest chamber, well-functioning chamber that you're ever going to see. We also were looking at what's the signal magnitude. Can we get enough signal from this to provide you with accurate measurements? Will the SNR be sufficient for the intended use? And we're quite happy with what we came out with on the other end of that design project. So strengths of the A26 is it is a reference class ionization chamber. It was designed to be that way right from the start, based on the findings from Jessica Miller's thesis. The spot size is uniform, independent of orientation. And another strength really is that ion chambers are familiar technology for most physicists. It's something we've used for our entire careers, and we're quite comfortable with that. Limitations of the A26 is that it does require corrections to account for that air volume. It's an ionization chamber. That's one of the limitations that we come across every time we use an ion chamber. I haven't talked about kilovoltage X-ray fields. That was all megavoltage we were looking at beforehand, but I do want to touch just briefly on small fields that are kV X-ray fields. We have a very small parallel plate chamber that's designed, again, in the end-on orientation, a little bit like our scanning diode. So your beam should be coming in this way, aimed at the chamber, but it's called the Exradin A20. And it's a low energy X-ray chamber that was specifically designed for small radiation fields that are kV X-rays, stereotactic fields, and TG61 compliant superficial skin therapy measurements. So it has just under a 2 millimeter collection diameter, and it has excellent energy response across the range of kilovoltage energies from 20 keV all the way up to cobalt 60. I'd be a little remiss in talking about small fields without bringing up our electrometers. I mentioned that you need to have something that is accurate and sensitive enough for the measurements you're making. We have two that I'd like to point out to you today if you're not familiar with them. The Max 4000 Plus is a workhorse. It is a fabulous chamber that's going to last you years. It's just a single channel reference class electrometer, but it has a wide range that it can be used both for current, low and high range currents, as well as charge collections. The Supermax is our top end electrometer. It's a dual screen with a dual channel with a touchscreen interface. Each side can be used independently if you want to put a diode on one side and an ion chamber on the other, or a big ion chamber for background and a smaller one for measuring in field. You can do that with this chamber, or just 2 points within your field. It also has a very short warm-up time, so it's nice if you need to make a measurement quickly and you've forgotten to plug your chamber in and wait those 10 minutes for it to warm up, or whatever it happens to be for your electrometer. Both of these electrometers have an industry-leading 5-year warranty. We have been making electrometers for a long time. We're very good at it. Not too modest in saying that, I guess, but we are very good at this. We've been doing it for a while, and we stand behind those. So a lot of information I've thrown at you. I hope you found it interesting. Together we can conquer this challenge of small field dosimetry, and we are proud to be working with you. The Standard Imaging family is excited to be your partner in making small fields happen, making them accessible to your patients, and helping you be comfortable with that as well. So if you want more information, please visit us at standardimaging.com. If you go to the /welcome page, that's our Astro landing page, and it lists the rest of the special webinars that we're offering throughout Astro. You can always reach out and contact us though. Find your sales rep if you haven't yet at sales@standardimaging.com. Or if you can't remember their email or whatever, then that one will get to them. My email address is sholmes@standardimaging.com if you have questions specifically for me. So with that, I'd like to thank you very much for your time. I think I saw just one question so far, which is whether the slides are available for download. We don't usually provide those, but if you want to reach out to me specifically, if there's something in particular that you're looking for with out of my slides, I would happily work with you on that. So any other questions, please let me know. Please feel free to type them in now. Otherwise, enjoy the rest of your day, enjoy your weekend. I hope you enjoy Astro, find some good talks and some good products to look at. And please reach out to us at any point if you have any other questions. I'm not seeing any other questions come in, so thank you all one last time for your attention and your time here today. We really appreciate it from the whole family at Standard Imaging. Have a great day.